Hello, I'm Véronique Doquet from the Laboratory of Solid Mechanics at École Polytechnique in France, and I'm going to present the second part of a study devoted to phatic crack growth under cyclic mode 1 and static mode 3. It was run with a postdoc, Louis Petureau, who presented the first part of this work, and a PhD student, Benjamin Dieu. In the previous talk by Louis Petureau, you heard about two series of push-pull tests on notched cylindrical specimens with a fixed axial loading range and various values of static torque. He showed that in spite of an increasing ellipticity and eccentricity of the crack fronts, it is possible to analyze the test results thanks to a finite element model allowing us to compute K1, K2, K3 at any point along the front. And K2 was found negligible compared to K3. Topographic measurements on the fracture surfaces allowed us to analyze the local crack path and more specifically to measure the local twist angles that are plotted here versus the angular position. Based on the computed stress intensity factors, it was possible to show that the measured twist angles are much smaller than predicted by the maximum tangential stress criterion. Such a result was also obtained by Ourlier and Pinault in the 80s. They worked on two steels and a titanium alloy. And note that for nearly the same mode-mixity ratio K3 on K1, the twist angle is quite different in the titanium alloy and in the mild steel, which led the authors to conclude that phatic crack paths depend on the material properties and not just on the loading parameters. They estimated approximately delta K1 and K1 max on a twisted facet. The former is reduced by twisting, while the latter is increased due to the contribution of the static mode 3. The crack was then assumed to propagate along the facet for which the crack growth rate is maximum, and this growth rate depends on both delta K1 and K1 max. So they characterized the mode 1 kinetics of the three materials at various R ratios that were all positives, and they fitted equations including delta K1 to some exponent beta and K1 max to some exponent gamma. And you can see from this table that gamma is relatively important in the titanium alloy, but nearly zero in the low alloy steel. And the application of a maximum growth rate criterion yields predictions of the twist angles which are much more consistent with the experimental observations than the maximum tangential stress criterion. Now, in the present study, before crack twisting, the R ratio is -1. And since in the near threshold regime, phatic crack growth is faster for R equal to -1 than for R equal to -0.5 or 0, it implies that crack growth on a twisted facet with a lower delta K1 and a higher R ratio cannot be faster than on the normal plane. And so the maximum growth rate criterion predicts no crack twisting in this material. Now, twisted facets were also observed in specimens loaded in pure mode 1 in angular sectors where bending-induced compression reduces delta K1, and in these areas there is an increase of local crack roughness and local twist angles, very similar to what was observed in presence of a torque. So it seems that the local crack path is not controlled by the mode-mixity ratio and raises questions about the role of non-singular stresses. In 3D, there is not just one non-singular stress denoted by T and normal to the crack front. There is a second non-singular stress denoted by S, tangent to the front, and also a non-singular shear stress, but it's not relevant here. Cottrell and Rice have shown that a positive T stress favors crack kinking, and Xu, Bauer, and Ortiz have shown that a positive S stress favors crack twisting. The evolution of both non-singular stresses with crack depth for a circular crack in a cylinder loaded in tension was computed by Al-Ani. And here is a plot of the normalized values t square root of pi a on K1, which remains constant and negative, and s square root of pi a on K1, which is negative for shallow cracks but becomes positive above a relative crack depth a on W of 0.3. So in the present study, the rising tensile S stress should trigger crack twisting beyond that point, that is, beyond 2.1 mm crack growth from the notch roots. However, SEM observations show that crack twisting occurs much earlier for elliptical and eccentric cracks. So, to analyze this phenomenon, the opening and tangential stress profiles ahead of the front of an eccentric elliptical crack were computed numerically at various angular positions. At theta equal to 0, where bending induced compression reduces K1 to 0, both the axial stress sigma zz and the tangential stress are negative, so that no crack growth can occur. At theta equal to 48 degrees, which is the angular sector where crack twisting was observed, even in mode 1, K1 is still 0, sigma z is still negative, but now the tangential stress is positive, and it is actually the first principal stress, and it is cyclic, and this explains early crack twisting there. By contrast, at 90 degrees, K1 is positive, and sigma zz is higher than the tangential stress, which is less favorable to crack twisting. And it is even more so at 180 degrees, where sigma zz is increased by bending-induced tension. Another puzzling aspect of the fracture surface was the presence of up to 500 micron wide wear marks normal to the crack growth direction, while the torque remained nearly constant. To explain it, we used the data issued from the optical tracking of the crack sliding displacement, CSD, and more specifically the axial load, CSD loops, recorded at each cycle. On this example, you can see that during a given cycle, there is no sliding displacement as long as the axial load is negative, but a little bit when it becomes positive. But the most interesting fact is the progressive shift of the loops, or in other words, a ratcheting rise of the mean crack sliding displacement, plotted here versus crack depth for all the tests. And you can see that the ratcheting rate rises with the static torque. To analyze this phenomenon and to investigate the influence of the torque on plasticity-induced closure, an axisymmetric finite element model with a regular refined mesh near the crack tip was developed. Tension, compression, and torque were applied on the top line. Elastic plastic constitutive equations using von Mises yield criterion, isotropic, and nonlinear kinematic hardening were identified based on strain control tension compression tests and implemented in the finite element model. We checked that there were always at least 4 elements within the plastic zone. In the first stage, a stationary crack was considered and 90 tension compression cycles with a static torque corresponding to the experimental loadings were simulated. A ratcheting rise of the mean crack sliding displacement computed 4 microns behind the tip is indeed predicted, and if we plot the derivative of these curves with respect to the number of cycles, we can see that the higher the torque and actual loading range, the higher the ratcheting rate. For the stationary crack considered in these simulations, the crack sliding displacement tends to saturate, but for a propagating crack, it would increase due to a rising delta K1, rising K3, more and more plasticity, and longer crack, deeper crack. In these simulations, we considered a smooth and frictionless crack, but in reality the crack faces are rough. But the crack face asperities get sheared, and this limits the torque-induced rise in roughness-induced crack closure effects, and these effects should thus saturate at high torque, which is perfectly consistent with recent results obtained by Liu and colleagues. They reported a saturation of a reduction of mod 1 crack growth rate at a given delta K as the static K3 increases. The finite element model was also used to simulate crack growth by repeated node release to investigate the influence of a static torque on plasticity-induced closure. For that purpose, the crack opening displacement profiles was monitored upon unloading to detect contact at the first node behind the tip. On these examples, you can see that at the first cycle, before any node release, crack tip blunting at peak load is important due to monotonic plasticity, so that the crack is still open at 3% of the maximum load. But after a certain number of nodes released for the same delta K, blunting is less pronounced and closure occurs before complete unloading. The rise of K closure on Kmax with a number of nodes released was computed for r equal to 0 or -1 for a given delta K1 and for various values of the torque until a steady state was reached. The higher the torque, the larger K closure on Kmax, and the steady state values were used to compute U, the ratio of effective to nominal delta K. Here is a plot of U normalized by its value in pure mod 1 versus the static torque for r equal to 0 in dotted lines or -1 in full lines, and for two values of delta K in blue and orange respectively. The normalized U drops as the torque increases, which means that a static torque enhances plasticity-induced closure, especially at low delta K. The effect is more pronounced for r equal to 0 and tends to saturate at high torque. So it's time to conclude. We've seen that the crack paths in magnetic steel circumferentially not cylindrical specimens loaded in tension compression and static torque did not match the predictions of the maximum tangential stress criterion, but seem more consistent with those of the maximum growth rate criterion. Bending induced by eccentric crack growth enhances the effect of a non-singular stress tangent to the crack front, which triggers crack twisting even without any applied torque. A static torque enhances plasticity-induced closure effects, especially at low delta K, and triggers a progressive rise of the mean crack sliding displacement and shearing of crack face asperities. And the effects of a static torque on roughness and plasticity-induced closure effects, and thus the reduction of the crack growth rate that it provides, tends to saturate at high torque. Thank you for your attention.